Welcome to the AIP Open Seminar today. And my name is Motoaki Kawanabe. I am the leader of the Information Integration for Neuroscience team. So here are some important notes about this seminar. So reproduction is prohibited. Reproducing all or any part of the content is prohibited without author's permission. And this seminar will be recorded and the video will be available on the RIKEN AIP website later. And if you have any questions or comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions and comments in the box. Okay, so this is today's schedule. And first, I will briefly introduce our Information Integration for Neuroscience team. And then 3 researchers of our team, Dr. Raima Kobra, Dr. Junichiro Hirayama, and Professor Aopo Hibarinen, will present their recent achievements. Okay, so let me start the team introduction part. And I also belong to Advanced Telecommunications Research Institute International, in short, ATR. So first of all, I will explain the backgrounds of our research. So as shown in this plot, a number of workers with mental disorder is increasing year by year. And this causes escalation of mental health care costs and lack of necessary labors. And Oracle AI at Work Study 2020 found in total 78% of 78% of workers suffer psychologically from the COVID-19 pandemic, such as depression, burnout, and stress. And 76% of them also believe the effort of their companies for mental health care protection are not enough. And the bottom figure tells workers embrace technology and AI solutions for supporting their mental health. And surprisingly, the statement was very surprising to me in particular. So as you know, companies perform self-administrated stress check about once a year, but they are very subjective. And instead, so as shown in this result, workers expect more objective and effective methods, such as health monitoring based on biomedical information sensing and AI, and on-demand mental health check and counseling. So we think brain signal is very important for such mental health issues. So in order to solve some mental health issues, we are developing monitoring method of negative mental states and excessive cognitive workload based on electroencephalogram EEG and the other biomedical signals, ambient information. And so EEG is inexpensive and possible to measure signals in a real-world environment and has high temporal resolution. But its drawbacks are limited information about brain activity and non-stationarity. So on the other hand, functional MRI can measure brain activities with high spatial resolution in 3D. And furthermore, fMRI connectivity biomarkers of mental disorders have been reported. But it's a large and expensive device and cannot be used directly for our purposes, unfortunately. So to alleviate these drawbacks of EEG, So we utilize simultaneous EEG and fMRI recording dataset provided by ATR. So in the first years, we focused on constructing better EEG decoding methods, in particular by transferring fMRI decoding and biomarker results to EEG based on such simultaneous recording data. So since properties of EEG and fMRI are quite different, so linking them is not easy, but possible, we think. So in fact, so this paper proposed EEG fingerprint to estimate fMRI signals of a specific brain region from EEG. And the authors also validated its usefulness by a large-scale experiment of neurofeedback for reducing stress. Okay, so the current state and challenges in neurotechnology are nicely summarized in this opinion paper. So, so these guys claimed one of the grand challenges is designing robust and reliable neurotechnologies in real world. And according to them, current issues are low accuracy in decoding users' mental states and sensitivity to noise and artifacts, especially in the wild, and non-stationarity and subject variability of neurophysiological signals. So I experienced these issues already in 2012, but they have not been solved completely yet. I also remark, because of these issues, there have been quite a few reports saying so deep learning approaches cannot improve substantially over conventional machine learning methods, as shown here. Okay, then so these authors defined sub-challenges to be tackled in the neuroergonomics field. And eventually, our research activities so far are mainly classified in the second and third sub-challenges, namely specific and robust biomarkers based on neuroscience, and neurophysiological signal decoders require little or no calibration time by transfer learning. Okay, so next, I will introduce 3 earlier results which want to be covered by the other authors, other presenters. Okay, the first one is an EEG representation method called SPLICE, proposed in this paper. And it is multi-layered independent component analysis inspired by 2 knowledge from fMRI researches. And first, so we can recover the sub-network structure in the brain by clustering envelopes of neurophysiological source signals. And second, the connectivity across these subregions are different between mental disorder patients and healthy persons. And by applying this method to so EEG fMRI simultaneous recording dataset, we could extract intermediate units of this model, which correlate with all the signal of fMRI resting state network like this. And further, so we also found a case where one splice component show somewhat similar characteristics characteristic to the connectivity used for fMRI neurofeedback in this proposed or done in this paper. And finally, so ATR tried EEG neurofeedback experiment based on splice, and a paper is under revision. Okay, the second one is analysis and visualization method of subject variability in connectivity between brain functional modules. So we call it modular connectivity factorization, in short, MCF. And so usually about 100 regions of interest are taken to calculate functional connectivity or correlation matrices like this. And since the number of elements of such matrices exceeds 10,000, so it is hard to visualize and interpret results. So the method MCF simultaneously runs a small number of modules and the subject variability in low dimensional connectivity matrix between modules. And so this is a result of 4-module case obtained by applying MCF to fMRI big data set with 1,000 subjects. Okay, and so these brain-like plots are the masks of the modules, and this is the modular connectivity matrix across these 4 modules. And the 4 modules are very similar to some resting state network. These networks shown here. And if so by calculating the modular connectivity graph, so individual modular connectivity graph of each subject, and sorting them along the component score, then we see the modular connectivity graph varies from healthy patterns with negative connectivity indicated by purple to the healthy, so patient-like patterns with no or positive connectivity indicated in orange. Okay, the last one is analysis of subject variability of brain function patterns common across behavioral states. So the method common neural modes was proposed by Takagi et al. 2019 as an international collaboration. And previous researches had focused on properties unique to a particular state, for instance, a resting state. So instead, the CMN common neural modes takes the multiple connectivity matrices during various or different behavioral states like resting state, language tasks, or motor tasks. And multi-set CCA extract factors of brain functional connectivities common across various behavioral states. So by applying the CMN methods to fMRI big data set, 3 common neural modes were identified as shown here. And so each factor was interpreted from correlation with indices of cognitive function, like fluid intelligence, or language ability, or sustained attention, etc. Okay, so at the end, so I will discuss a bit about our future direction. So some researchers have worked on developing the neurotechnology in daily situations at work or at home. However, from my experiences, so social implementation of such applications with wearing the EEG cap always is unrealistic within 5 years. So we started the second stage research towards integration of behavior and biomedical information from wearable and ambient sensors with mental state estimation by EEG I explained. And for instance, use case image is like this. So workers monitor their mental state closely with wearable sensors. And when getting some alert, they go to industrial physician and have mental health check with EEG and so on. Okay, that's our kind of future goal. Okay, so except for the 3 researchers who will give presentation today, so we have 3 more visiting researchers, Dr. Taiki Miyanishi and Professor Katsushi Ikeda and Dr. Ricardo Monti, who stayed in our team for 10 weeks in 2019. Okay, so finally, I have a small announcement of call for collaboration, in particular with machine learning experts at Linear AIP. And so if some of you are interested in these research directions, so please contact me. Okay, that's all of my talk, and thanks for your attention. So there is no question so far, and also I use up my time, and so I'd like to move to the next talk. So Kobra-san joined my team since last November, and so he studied at the Graz Technical University of Graz, which is on kind of the hotspot in brain-computer interface. And today he will explain his new and old researches. Please start.
Okay, thank you very much for the introduction, Sensei. I will be talking mainly about intercession and also application transfer from 2 perspectives. One's to facilitate user training in the end user, so paralyzed individual, and in the other, from the other perspective, on extending Riemann and tangent space methods to obtain patterns or mixing coefficients of sources to improve model interpretability. First, I'd like just to quickly fill in maybe a bit in terms of the sources of MEG variability and non-stationarities that Kawanaba-sensei already outlined a bit in his talk. EEG is typically considered to be a linear mixture of instantaneous mixture of multitude of sources, which is typically considered an ill-posed problem, where the activity that we measure at channels, multiple channels, maybe depicted here a bit, in a segment, index I maybe here, is a linear mixture of some latent sources and some additive noise. Sources are ideally mainly brain activity or cortical activity that the EEG or MEG is sensitive to, but unfortunately, it's also capturing environmental noise sources, other physiological sources like muscular activity, eye activity, heart-related activity, and also movement artifacts, which can be stationary, transient, or a mixture. Then we have a number of other confounding factors, which can be of technical origin, like at the scalp electrode interface, change of impedance, or also change of geometric configuration due to movement of the subject with respect to the sensors, or different sessions, and also various other recording devices. But also what's sometimes considered artifact, or sometimes the very signal of interest, are mental drifts or mental changes, for example, fatigue, or also maybe some emotional state changes. And big factors of variation are also individual differences or inter-subject differences. Typical use cases, so these are the challenge, large challenges for transfer learning in the MEG setting. A typical use case for transfer learning in the context of brain-computer interfaces, particularly for multi-memory BCIs, is to cut calibration time of an individual in order to facilitate feedback training. And in the first part, I will be mainly focusing on multi-memory BCIs, which basically try to detect specific changes in some brain rhythms associated to really distinct tasks. So for example, if a person imagines to squeeze a ball, a stereotypical pattern would be that in the brain rhythm, for example, mu rhythm, in the motor cortex area would be a power decrease. These effects are detectable in around 70 to 80% of humans. And the main factors of variation that limit transferability are individual differences, and also these non-stationarities due to differences in the electron configurations, environmental noise factors, mental drifts, and so on. And lastly, we also have very heterogeneous data, so different recording systems, also reference electrode configurations, and the data that we have so far is also rather scarce because it's still very costly to record EEG activity during these mental tasks, and particularly in terms of recording time. If you think again about this multi-memory setting, we have typically a two-learner system, which is a closed loop system, where we have the human on the one hand that tries to generate these patterns, and then acquire the skill of multi-memory, for example, and also then via feedback training refine this skill, so basically enhance these patterns that the person can generate. And on the other side, we have the computer, where we have this pattern recognition or machine learning algorithms that try to detect these modulations and provide feedback to the user. For example, whether, very simplistic case, whether a multi-memory or specific mental task was detected or not. When we talk about closed loop training, we have unfortunately also very limited data available, mainly on single session or few session experiments with healthy students because of the simplicity to conduct experiments in this setting. In terms of long-term, like over several months and multiple sessions, and particularly also with end users, there's very few works available so far. This was also strong motivation by the ETH Zurich to found the Cybertron competition, which is a competition that takes place every 4 years, where with the goal to facilitate exchange between technology providers and end users. And one of the disciplines in the Cybertron competition is a brain-computer interface race, where then the teams try to compete with each other. And here I have a pretty short video where the end users try to control an avatar around the racetrack with 4 different commands, which should be triggered, of course, with high accuracy. So we want to have many true positives and really as few false positives as possible, because otherwise this would result in a penalty. For example, here, the straight track, the user should have not sent a left or right turn signal here. Okay. And in the first part of my talk, I will be focusing on a single case study that we published earlier this year in Frontiers in Neuroscience, where we have basically summarized our team's effort to prepare a tetraplegic person to compete in the Variational Inference race. And the main methods that we resorted on, or ideas that we resorted on, was to facilitate closed loop training, also do intersession application transfer of the model parameters, and to then within session decode adaptation. The study period lasted actually a bit more than a year, from fall 2019 to the late fall last year. And in this paper, we then analyzed 26 recording sessions. The approach was that we used 4 distinct mental tasks to map this to the 4 possible commands for the game. Then we considered our approach to kind of applications. One was a very well-defined controlled standard BCI paradigm, which we use for feedback training. And then the ultimate application was this brain driver game, which you have seen just before. In terms of methods, we resorted to very standard establishment methods where we used fixed spectral filters to extract activity in 4 distinct frequency bands and alpha beta ranges. Then we used the standard component-based methods like common spatial patterns, CSP, to extract activity of sources of interest, which are predictive for the classes, computed log band power features for these sources, and did then feature normalization in an unsupervised adaptive way. Within each session, finally, linear classification. The workflow within one session was as follows. We had some preparation where the model was pre-trained with data from 5 previous sessions. Then we had a short calibration period where the standard BCI paradigm was used to facilitate feedback training. So we have some trial structure with different classes, and then we have also immediate feedback from the computer, basically whether the intended class was detected or not. After calibration, the model was retrained with this additional data, and then there were several games of this brain driver game, and we have an unsupervised adaptation of these normalization parameters to compensate for potential covariance shifts in the data. The ultimate performance evaluation criterion is, of course, the game runtime, where we observed a significant decrease in the average runtime from initially around 255 seconds per game on average to around 225 towards the end of this period, which is around 8% increase. Unfortunately, there was still large variability within single games within a session for around 22 seconds initially and also towards the end. So there's still quite some demand for improvement, I would say. What was not intended but interesting to observe was even though there were long breaks, COVID-related last spring, here 4 months without any training, the pilot could still maintain the skill level that he had before. In terms of neurophysiology, this is rather difficult to show usually in a BCI setting, but since we recorded here a long-term experiment and also had 26 sessions, we could actually show that there was also on the neurophysiological level a training effect, particularly related to the classes feed and subtraction, so 2 classes of the 4, where we had in the first 8 sessions on average here in the lower alpha frequency band some initial difference in these 2 classes in terms of power modulations, which you can see here intensified during the training time. Similar effects in the upper alpha frequency band. With regard to 1 class, we did not see any training effect. And also interesting with regard to the 4th class here, we observed initially no effect. And then over time, we observed the emergence of a small, here this power decrease in the central electrodes, but rather weak effect. To quantify this, we computed between class distance ratios, where we saw the strongest effect initially already in feed subtraction of around 2, which increased to around 2.5 during this training period. the trends or the effect of time was significant here. And then also with regard to subtraction word, we also saw initially no effect and then a slight improvement around 1.3, which is small but significant. And then for the feed word, we also observed an improvement. Then with regard to classification, we were interested in the effects of transferring and also indicating the stability of the patterns. Therefore, we trained the model parameters once at the single session level. So when we used the cross-validation approach to predict, to get an estimate of the performance, where we use just the within session calibration data. Then the transfer model would correspond to the model that just considers the data of 5 previous sessions and is then tested directly on the current session's data. And the combined model uses the training data of both methods to learn the model parameters. As expected from previous research, we observed that this combined approach yields a significant improvement upon the 2 other methods, around 5%. And we also observed here in the classification accuracy a significant effect of time, which matches and is actually significantly coupled to the increase in neurophysiological strength of these patterns. We did not see any significant difference in the average classification accuracy between the transfer and single session methods, which can be attributed to 2 effects. First hand, actually the patterns that the pilot learned were then stable across sessions. And the second effect is, of course, we used little calibration data, so there was actually a rather small amount of data available for the single session model. That's why we observed also higher variability. Okay, then altogether, in the first part, we could show that this combination of closed loop training and transfer learning facilitates actual user training in this tetraplegic user. We could show a scale refinement effect for the feed subtraction class and also a weak skill acquisition class, so where we have the emergence of a new pattern with training from word versus subtraction feed classes. And altogether, these improvements in the application calibration paradigm could be transferred and also to improvements in the final application in terms of game runtimes. Naturally, this is a single case study, so it's difficult to generalize these effects to new population or new participants. And unfortunately, we observed also a small slope in terms of just 2.4 seconds time improvement in game runtime per month. And in terms of robustness or variability within session, there was no real improvement, which would be highly important for a competitive setting to have a high precision and less variability. So there is a high demand to improve techniques. On the one hand, from the user learning or training paradigm, so coming up with more paradigms which are more evolving for the pilot or user, and on the other hand, in terms of methodology, of course. Let's focus more on the second aspect, so in terms of methodological improvements. How can we improve performance? So what we would like for the pattern recognition algorithms, we want to have state-of-the-art performance, but in order to also interpret the results of the model in terms of training effect, but also neurophysiology interpretation, we want easy model interpretation. And in our recent paper, which will be published in this year's AIP UBC in November, this year we focused on Riemann and Tangen space methods, which have been shown in the last years to reach state-of-the-art performance in the BCI setting, for example, multi-metric, but also other paradigms. And also very recently in the biomarkers, for example, in age prediction and also in antibody prediction. But they lack so far easy intuitive way to obtain model interpretability. In a nutshell, in the Riemann and Tangen space methods, we start from covariance matrices, which could be the covariance between EEG sensors in certain segments. And they are lying ideally on a SPD, so symmetric positive definite manifold. And then the idea of Riemann tangent space methods is to project these methods at tangent space at a certain point, mostly the geometric mean of the data set. And then in this Euclidean vector space here, do off-the-shelf linear classification algorithms. The generative model that we considered was similar to previous works. So we considered encoded source signals, SI of t, with p dimensions. P is the number of channels. So we have here a full ring, well-defined problem like in IC, and we have a fixed linear mixing matrix A. And then we also consider a log linear relationship to the target variable in terms of source powers. So the powers of these encoding sources are then in terms of log linear related to the target variable. Given this generative model in a set of sensor covariance matrices, their geometric mean, one can actually show that the tangent space projection at this geometric mean is and combination with any linear estimate that maps from this tangent space or this vector space to the space where our target signal is defined is actually a consistent estimate of the target variable. And we are now particularly interested in the model parameters for the linear case and the weight vectors. And what we proposed is, given this RTS model parameters W, we would like to identify the mixing matrix A and the contributing sources. So here we have our generative model and our source signal. So we would like to identify the mixing coefficients A and also the source contributions. So basically coupling, define the coupling between the source power and the target. The approach that we presented is to, in the linear vector space and the Riemann tangent space, to compute the giving the weight matrix, weight vector, and also the observation covariance matrices, compute the associated patterns, and then basically back project these patterns to get covariance matrix in the SPD space, and then we could show that the encoding mixing coefficients and also coupling factors or encoding source contributions can be obtained by solving the generalized eigenvalue problem between the projected patterns and the geometric mean covariance matrix. In a couple of simulations, we simulated some model violations. Mainly, we considered here a very simple 5-dimensional case with one encoding source. Today, I would like to focus on one particular violation, which is very common as intersubject, also intersession transfers, where we have session or subject dependent mixing matrix, which consists of base mixing matrix, and in our case, some simulated additive noise, IAD, with some variation in noise strength. When we then look at the goodness of fit in terms of mean absolute error between the true target signal and the estimated one, we see that both the Riemannian method, the low noise case, and also the representative component-based methods, the source power co-modulation, obtain zero or almost negligible error. And as the mixing matrix noise increases, we see that actually the Riemannian proposed method, Riemannian tangent space method, has a higher robustness to this noise compared to the standard component-based method. And just for simplicity, using just diagonal elements of the covariance matrices, which corresponds to the power of the EEG sensors, is obviously not a consistent estimator for this generative model. And what we were interested in then is how these effects translate to our estimated patterns. Therefore, we used here 1 minus the absolute value of the cosine similarity between the true pattern and the estimated pattern. And we also saw basically that this robustness property from the target signal also nicely translates to the estimated patterns. Then in terms of real MEG or EEG data, let's focus first on a regression problem, a dummy problem, where we have a single session, single subject MBG experiment, which is basically highlights the importance of model interpretation. The data is publicly available on the Field Rate Toolbox website and is focusing on the effect called corticomuscular coherence, where the goal is to use covariance matrices in the beta frequency band to predict the envelope of EMG signals, so electromyography, so vascular activity, basically. Here we have a single trace, for example, of the EMG envelope. In black, the target signals, contraction or no contraction here. And then we have the two estimates with the component-based regression method and the Riemannian time space-based regression method. Both methods achieve rather high performance for MEG, with variance explained for the Spock method with 4 components of around 0.5, and similar for the Riemannian method, also around 0.5. So this is very suspicious because one would usually expect a weaker coupling in EEG, MEG around 0.3. Then when we look at the patterns for the component-based method, we have strong coupling in the first eigenvalue, first source, and then quite a strong increase. And the first source is typically topographic patterns associated to IO artifacts. So this model performance was mainly driven by artifacts, highlighting the importance of interpretable methods. However, there is also some coupling in meaningful sources, like here in the motor cortex, then we have some visual source, and then the other hemispheres motor cortex. If we go to the Riemannian tangent space method, we also see strong agreement in the first source. So performance is mainly driven by artifacts in this case, but we also can see that our proposed method also can nicely identify these encoding sources, like the Spock method, up to, of course, ambiguity of sign. And since we estimated here more components, we can also identify here maybe some additional source in motor cortex, parietal area, and also maybe some frontoparietal source here. To the second experiment, which is then more interesting in terms of this model violation, so inter-session transfer. Here we analyzed basically the data set that I've been presenting before, where we have 26 sessions. In this setting, we just considered the two most discriminative classes, so feed versus subtraction multimetry, these 4 frequency bands that we used before, and the transfer setting where we do leave one session out cross-validation. The component-based methods that we used in the earlier work, CSP, was not really affected by the number of components, so peaked at around 10 for 10 components with 90% median classification accuracy. Whereas the Riemannian tangent space method peaked at around 18 components with 94%, and this was then significantly different across the sessions, indicating already or confirming that this Riemannian tangent space method is more robust to these model violations that we have also seen in the simulations. In terms of patterns, we can see that both methods agreed in the first source, which were the most discriminative here, in the lower frequency bands, which also agree nicely with the average class effects that we observed in the previous work. In general, we see for the Riemannian tangent space method, the reef patterns, more smoother patterns which have more dipolar origin or dipolar like shape, which indicates usually better decomposition compared to these patterns estimated for the CSP method. And notable is also the second effect is for this CSP type method, we did not really see any strong coupling in these beta frequency ranges here. Whereas the Riemannian tangent space, the reef patterns, have also a coupling effect which is almost as strong as the second source in the alpha frequency bands. So this additional coupling can potentially explain why the Riemannian tangent space method improved upon the CSP type method in the classification setting. Okay, to wrap up the second part, we started here with the linear entanglement space methods, which offer state-of-the-art performance in BCI, but lack model interpretability. And based on the model parameters of linear entanglement space models, we showed that one can identify actually the mixing coefficients of the encoding sources and also the coupling strength. And what we also showed that this robustness property of the linear entanglement space estimator in terms of target signal estimates also translate to the estimated methods. In terms of future directions, we are now interested in or working on combining this linear or Riemann entanglement space methods on the SPD manifold with feature learning techniques like neural networks. And we are also interested in working on improving robustness, particularly for the higher variability in the inter-subject transfer case. Okay, I think that's it. Thank you very much for your attention. If you have any questions, please feel free to ask.
So you have a question from Tomek?
Okay. Just need to open it. Question 2.1. So thank you, Tomek, for your question. Usually at each BCI session, electrodes are attached at a slightly different location or with varying impedances. Do you somehow normalize these problems during transfer learning, taking into account previous subjects BCI sessions? Yes, in the first part, we actually took this into account. There we used this unsupervised feature normalization, where we use basically session-specific estimates for the features to do standardization. And in the current session, where we have incoming data, we then adapted these normalization parameters with exponentially estimates. So basically running estimates of the statistics. I hope this answers your question. Thank you. Perfect.
Okay, then it's time. And so thanks, Kobra-san. And so I'd like to start the next presentation. Okay, so let me introduce you. And so Hirayama-san was a research scientist until 2020. And then he got position at ICE as a senior researcher, and he moved to there. And but we are collaborating together. And so today, he will explain his the mixed shared component analysis, partly published at NeurIPS. So Hirayama-san, please.
Okay, thank you. So my name is Junichiro Hirayama, and so as Kanabe-san introduced, I am a researcher at AIST, and now a visiting researcher at Weekend AIP. And so today, I would like to talk about recent studies which I have done in collaboration with those people. And actually, Dr. Yu Takagi was the main contributor of these studies. And I myself contributed mainly in the methodological side of data analysis. And other people mainly to experiment and data acquisition, and also neuroscientific data analysis. So let me begin with some background. So as you know, the brain is a kind of a network system consisting of a huge number of neurons. And the neuron receives sensory inputs, process the information in the input, and finally output motor commands to make some actions. And the processing is mediated by interactions of neural populations across different brain regions. And each region is known to have some specific functions different from each other. And so the interaction between the brain regions are actually crucial for the brain to perform some integrated function toward in a unified way toward a behavioral goal. And so a popular approach to understanding such a multi-region interaction in the brain is to measure so-called functional connectivity between regions. And the idea is quite simple, and we measure the neurons or neuron groups activities within each region. And in the in the simplest situation, we compute, we take an average of the neurons within each region and compute the correlation between the average time series. And of course, this correlation does not necessarily mean there is physical or neuronal interactions, direct interactions between these regions, but at least it can be an important clue to an investigation of multi-region interactions. And in practice, many types of neural recording or imaging techniques are available to measure neural population activity. And a direct way is to insert electrode into animal brain and measure the neural spikes or associated changes in the electric potential. And actually, this is the main topic of today's talk. But for human studies, it is often difficult, usually difficult to use such strongly invasive techniques. So usually we consider a more non-invasive type of brain imaging techniques. And in the end of this talk, I will also briefly touch on fMRI data analysis of human brain activity. Okay, so now I will introduce some more specific motivation. And as I said, the basic method for measuring functional connectivity is to first take an average within each region. But this is probably not an optimal way, because the properties of the neurons within each region is not necessarily uniform. So several studies used more advanced types of multivariate data analysis methods that is dedicated to the analysis of paired datasets. And these are three examples from animal electrophysiological studies. And these three studies commonly used linear dimensionality reduction techniques, such as principal component regression, reduced rank regression, and canonical correlation analysis. And the data here is typically the short-term firing rate of multiple neurons, and each column in one panel corresponds to one neuron time series. And then I will skip the details, but these methods commonly learn linear association between the regions, reducing the dimensionality of each region in a method-specific way. But in practice, those previous methods are not actually very suitable for if our goal is to analyze task-induced connectivity. And this is actually quite a common situation in neuroscientific experiment. And in particular, a task often involves multiple relevant variables that may affect neural activities. but their effects on the connectivity are not well dissociated if we use existing conventional techniques. And for example, this is an illustration of perceptual decision-making task of mouse. Here, a subject is trained to respond to visual stimuli to make some decision or action. In this case, the decision or action is turning the wheel to left or right. And in this case, the stimulus and decision types are the task variables of interest, and how the connectivity relies on those variables is of great interest. And to address this issue, we recently proposed a method called demixed shared component analysis, or DSCA. This is quite a simple technique based on reduced rank regression. And in the usual case of reduced rank regression, we solve a linear least squares regression problem from source region X to target region Y, given a rank constraint on the coefficient matrix. But in this case, the regression is now actually trying to explain all the variability in the target data without caring about the task labels associated. So instead, our DSCA DSCA explicitly uses the task labels. Here, the two labels, the stimulus and decision. And then it first decomposes the target Y into so-called factorial effect using the idea of analysis of variance. So in this two-way example, the target data Y is decomposed by ANOVA into 4 terms, and 3 of which are task related. And the last one is just an error, not related to task. And the first 2 are the main effects by stimulus or a decision, and they are each of them is a function of a single task variable, and the interaction is a function of both variables, and this is usually defined to be orthogonal to the main effect. So using the idea of ANOVA, we can decompose the variability of target in terms of its association with task variables. And then, given such a decomposition, we define our DSCA as a collection of reduced rank regressions applied to each term separately. And so we expect each R to extract a few dimensions or components that are specifically associated with each task variable or the interactions. And so this is quite a simple technique. And the essential idea was actually originated from a previous study, which developed a method called the mixed PCA that is applied to a single data set rather than paired data sets. And this method, the difference between DSCA and DPCA is that the DPCA applies the similar scheme between the same region. So the target data is the same region, but decomposed by ANOVA. So this is an extension of PCA, which is known to be equivalent to a linear autoencoder. From a more general perspective, our DSCA is a supervised linear dimensionality reduction dedicated to the analysis of paired datasets. And in particular, like the mixed PCA, our method focuses mainly on the multi-label situation and uses the idea of analysis of variance to enhance the interpretability of task-induced connections. Okay, but in practice, when to apply our method to real data, we further need some modification, or further needs some trick to be successful. As illustrated in this figure, the neural recording data is usually measured through a number of experimental trials, and the time in each trial is somehow normalized to define a common time course after a specific event at t equals 0. And the problem is that the activities of the two regions are often correlated only transiently, and the timing of correlation and their time lags, and also the causality direction are not known in advance. So previous study proposed to apply CCA many times for all the pairs of different time points between the two regions. Then the method produced a time-resolved connective map, which summarizes all the canonical correlations for all the different time points, time lags, and direction. So in our study, we also take the similar scheme, but now with DFCA instead of CCA. And using DFCA, then we can obtain similar time-resolved connectivity maps. But now we have multiple maps, each for a single factorial effect. And also we here use a reduced sample regression. So the map shows explained variance instead of canonical correlation. And overall, our proposed method is expected to reveal both when and what information about the information sharing between the regions. And so from next figures, I will show some simulation and real data result. But we have focused on the analysis of main effect, and so we will not show the third map about the cross effect of task variables. I'll first show you a simulation result. And here we virtually considered a situation of perceptual decision making. And simulated timeline is given in the right figure. And I'll skip the detail, but there are basically two task-related components. And the magnitude of the earlier component varied only with the stimulus levels. And the magnitude of the latter component varied only with the decision types. So roughly speaking, this setting intended to simulate directed interaction from X to Y and then Y to X, and between a sensory area X and a higher cognitive area Y related to decision making. So first, we applied the previous CCA-based methods to this data and found that the time-resolved correlation map showed two blocks of significant connections, which is actually what we expected from the simulation setting. But at this moment, the meaning of the two blocks is not necessarily clear if we do not know about the setting. But in contrast, using our method based on DSCA, the two blocks are well separated into the two maps, and each map is now explicitly associated with one task variable. So the interpretation is made much more clear now. And next, we also analyze the real neural recording data, which was acquired in a previous study about monkey's decision making. And here, the original task is a little bit complicated. So we used only a small part of the data for basic validation of the method. Here, in this task, a subject is trained to open picture queues at the 4 spatial locations. And opening this one picture queue, the subject will know a specific real-world values that would be obtained by subsequent choice tasks about the spatial groups, left or right. So basically, when opening the first queue, the subject needs to perceive and process the 2 task variables, here value and space, to prepare for later decision. So we only analyzed the time window just right after the Q1 onset. And we analyzed pairwise connectivity between these 3 regions of interest. And again, we first applied the previous CCA-based method and found that every pair of regions are somehow connected at some point after the Q event. And then we applied our method based on the SCA and found that we can further look into the details. So for example, at the top, the connection between DLPFC and SCC is now clearly separated into value-related and space-related connectivities, and which is roughly seen in the original result, but the meaning was not clear. And so now we can see some clear meaning here. And also at the bottom, we can also see a clear separation of value-related and space-related connections between OFC and DLPFC. And we can also see that this causal direction is almost from only from OFC to DLPFC, but this is somewhat bidirectional. And interestingly, in the original result, there seems to be no the cluster is seen only one, and so our result can give more interpretable and detailed result as compared to the CCA method. And this is the final part of this talk. And so far, we have assumed that the task variables are categorical. So I mean, the stimulus and decision was discrete and have only a few levels. And this is actually a basic assumption of ANOVA. However, in practice, this is sometimes quite restrictive assumption. And in particular, recent human fMRI studies use naturalistic stimuli such as movies and music to investigate the brain function in a more natural situation similar to our daily living. And in such a situation, we actually need to deal with many types of features like face, word, object, scene, etc. And they are not necessarily categorical and can be continuous. So it is important to dissociate their effect on connectivity by an appropriate method. So to deal with this issue, we recently developed an extension of the SCA called the Neural DSCA. This is actually an achievement outside the weekend, but let me briefly introduce using this opportunity. The idea here is again quite simple. So we just replace the conventional ANOVA model in the SCA with an advanced type of ANOVA called functional analysis of variance, or FANOVA. In this method, the target activity is decomposed in a similar way to the conventional ANOVA, but now the main effects can be a nonlinear function of single feature vector, continuous feature vector, and the interaction effect is also a nonlinear function of the pair of the feature vectors. And given some integration constraint to ensure the identifiability, we can theoretically identify this decomposition. And in our implementation, we used a neural network based technique that are recently proposed. We term the method neural DSCA. And we applied our NDSCA to a movie watching fMRI dataset and analyze pairwise connectivity between 10 regions of interest, as given here. And in this case, we didn't consider any time lags because of the low time resolution of fMRI. And the two directions of reduced rank regression between two regions are averaged. And so the connectivity is undirected. And here, PPI is an existing technique based on region average. And we also developed a kind of a simplified version of our method, but I'll skip the omit detail. And the leftmost panel shows the result by standard reduced rank regression. Then, as you can see, only NDSCA gives a clear, strong connections between some particular regions of interest, and which is induced by phase stimuli, a phase variable, and this is induced by the word value. And the pattern of connectivity for phase essentially indicates interaction between visual areas like V1 and phase areas and other areas. And that this connection for word indicates indicate the connection between temporal areas and other areas. So they could be some meaningful result, but we actually still need to investigate in more detail. Okay, so this is a summary of this talk. So we proposed a method called DSCA as a method for pairwise dataset analysis. And we also proposed an extension called function neural demixture shared component analysis using the idea of functional ANOVA. And we also demonstrate the method with real data, including both animal and electrophysiology data and human fMRI data. Okay, thank you. That's it.
Thank you very much. And if you have any questions, please write in the Q&A box. Okay, so I have one question. So in the second part as a neural DSCA, so you use the neural network, right?
Yeah.
And
yes.
I wonder, so how many data points you need to run a reasonable neural network used in this
I don't quite remember the number of data points, but this data is actually the fMRI data is recorded quite long during maybe a whole movie, so maybe over 30 minutes or so. So there are relatively many time points as compared to more conventional type of fMRI recording, I think.
That's
No, usually we need much sample to learn neural networks.
Okay. Okay, you have questions from Chibin?
Yeah. The question is DSCA linear dimensional reduction method? Do you think nonlinear dimensional reduction method like DNN is necessary or not? To my understanding, at this moment, DSCA is linear dimensional reduction of each region. And nonlinear dimensionality reduction could also be combined with the idea of ANOVA decomposition. And in the latter part, the dimensionality reduction part is still still linear, and ANOVA part only the ANOVA part is replaced with nonlinear technique. Am I answering correctly? I'm not sure, but it's my answer. Okay, thank you.
Okay, then it's time to start the next talk, and so thank you, Hirayama-san.
Thank you very much.
So the last talk will be presented by Professor Apo Hivarinen, and I don't have to introduce him really, but so he's a really famous machine learning researcher nowadays, and also he joined this seminar from his home country, Helsinki, Finland, and maybe it's rather morning, I think. Okay, so yeah, so he talked about his recent advances on nonlinear independent component analysis and identifiability and likelihood, and maybe the relation to DeepNet or something like that. And I'm very looking forward to your talk.
Okay, good morning, everybody, and thank you for inviting me to give this talk. So this talk will be actually very theoretical. So I suppose, can you hear me well?
Yes.
Okay, good. So this talk will actually be quite theoretical. I have almost no results on neuroscience or anything. In fact, in the original title, I promised to talk about nonlinear independent component analysis, identifiability, self-supervised learning, and likelihood. And I realized that's a bit too much for one talk. So I will only be talking about identifiability and likelihood in this talk, especially emphasizing the fact that we can now do likelihood inference for nonlinear independent component analysis. So the starting point is that people are talking a lot about what they call disentanglement, which in deep learning, which is something about finding independent factors. Now, in the linear case, there is actually a method, independent component analysis, which has been very successful and also a very principled method for doing that kind of a disentanglement. So then we, of course, would like to extend that to a nonlinear method. But a problem, which is kind of very well known for actually many decades, is that the nonlinear ICA model is not identifiable. That's a key concept that I will define a little bit later. But then there is a solution, which is several different solutions. The solution I'm talking about here is really about using temporal structure in time series, different kinds of temporal structure, or something which is a bit more general. So we started this project essentially with Morioka-san in 2015 using self-supervised learning methods. which are kind of a very fashionable way of doing deep learning and unsupervised learning. But in fact, what I will be talking about today is how to do something which I consider, which may be a better way of approaching the problem. I hope it's a better way, which is to use a maximum likelihood estimation. And I will talk about two different ways, two different models, basically noise-free and noisy versions of nonlinear ICA. In both cases, we basically run into various kinds of computational problems, and then I will talk about two different solutions to those problems. Actually, these solutions are partly well known, like VAE, and partly then actually applicable to many related models as well, not only IC. So the kind of key point here, or kind of the key starting point in this talk, is the idea of finding a principled method for representation learning. So this is, of course, a little bit subjective, not a very rigorously defined concept, but often people say that they want to do a principled learning. Well, I suppose in this case, my personal opinion would be that a really principled approach has the following three aspects, maybe more, which is that first we formulate the problem as estimation of a latent variable model, like in ICA. Then we have to show that the model actually is identifiable, that is well defined in the sense that you can actually find some of the latent variables or the posteriors. I will define that more precisely later. But then the third point, which I'm emphasizing in this talk, because it's basically new, something that we have only been able to do since very recently, is to then estimate these nonlinear ICA models by maximum likelihood estimation. So what is the point in this kind of a principled learning? Well, in some sense, I think that basically we have models, we have some kind of guarantees that these models make sense, because we are building them using the machinery of probabilistic inference. So the operation of the model, and especially then the learning of the model, are much more easy to understand, which makes them, to use a fashionable term in AI, perhaps more trustworthy. And especially then these models will be easy to combine with further modeling, further aspects, like we can introduce easily noise or incompleteness of observations, missing observations in the models. We can add various kinds of more detailed models of the latent variables, such as hidden Markov models. And then especially we can do inference with these models, like maximum posteriori or any kind of Bayesian inference for such tasks as denoising or filling in of points and so on. And last but not least, maximum likelihood estimation always has the promise of giving statistically efficient estimation. That is, we basically make optimal use of scarce data. Okay, so to start with a short introduction to a linear ICA, well, I suppose most of you have seen this model. The idea is that we have observed variables xi, where I is the index of a channel or observed variable. K is the sample index, which might be time or might be something else. And the idea is that we want to express these observations, this observational matrix, essentially as a function of certain latent variables sj and mixing coefficients aij, which kind of describe how the original independent components are superimposed or mixed together in order to obtain the observed variables. Now, importantly, we assume that these independent components or sources sj are statistically independent as well as non-Gaussian. And under those assumptions, then we have the fundamental result that the ICA model is identifiable. That means, so this is the key concept, one of the key concepts here, which is that it is well defined in the sense that observing only these x's, we can actually recover both the a's and the s's. There's, of course, a lot of models which actually try to have this kind of which estimate this some kind of a decomposition, maybe a matrix decomposition, but they are not identifiable in the sense that you can have many different a's, many different s's that express the data equally well. So this theory actually goes back to Darmois and Skytovich around 1950, although it was kind of popularized by Comon in the 90s. So what identifiability means in practice is that ICA can do something called lines of separation. So suppose we observe the four signals at the top, well, as a four-dimensional simultaneous time series. Now, if we do PCA on that data, what we get is this in the middle row, which really isn't something particularly meaningful. But ICA can actually find these 4 signals, showing that in fact the 4 observed signals are a kind of are basically mixtures of certain highly structured and possibly meaningful signals. So as a simple neuroscience example, well, you can just take MEG data or EEG data, input it into an ICA algorithm, and then you will find certain components which may correspond to brain sources. Here's an illustration where we did, well, actually an experiment where we took resting state data in MEG and put it into an ICA algorithm, and after certain kind of a stability analysis found that there's basically seems to be 9 somehow stable independent components in the brain. Interestingly, some of them correspond to well-known brain sources like visual areas, Rolandic areas, and so on, while others are less known. And so then that kind of suggests that maybe these less known sources should be investigated further. You can also do image decomposition with the method, but well, I will not go into details there. But so, nonlinear ICA, it is in a sense an unsolved problem. Well, maybe that's a little bit too pessimistic, but the point is that if you try to formulate a very simplistic, straightforward form of nonlinear ICA, then you run into problems. So if we simply say that the xi's are some arbitrary nonlinear transformations of independent components S1 to Sn, then, well, it is unidentifiable in the sense that you can find many different nonlinear functions f and many different independent components that equally well express your observed data with exactly the same statistical properties. That's illustrated here. So we have here 2 independent components whose scatter plot is shown here, and the data points are colored only for the purposes of visual illustration. Now we can have a nonlinear mixture of those components, which is, as you can see here, quite nonlinear. And then we can actually find independent components which are exactly independent and which have exactly the same statistical properties as the latent variables in the original model, which are plotted here in a scatter plot. But clearly these components here, these estimates, are not the same as the original components. So that is an illustration of the unidentifiability. We cannot actually find the original components. This was actually proven by Darmois in 52, showing using a very simple construction. He showed that when you have, in the basic case, just 2 variables x1 and x2, you can always construct a function g whose output is denoted by y, so that this new variable y will be independent of x1. It's by a simple construction using the conditional cumulative distribution function. So what that shows is that independence is basically too weak for identifiability, because now you could claim that any of the observed variables, like x1 in this case, is one of the independent components, because then you can decompose the data into x1 and other components which are independent. And so that's of course completely absurd to say that you can take any of the observed variables and say that that is an independent component. So that is how Darmois originally showed the unidentifiability. And this is exactly what we did in this illustration on the previous slide. We did this Darmois construction on these nonlinear mixtures and thus obtained the kind of wrong estimates of the independent components. But okay, that's not the whole story. So that proof by Darmois and that whole theory basically assumes that we have IID observations of the data. So there is nothing like temporal structure in the data. We just have independent observations of the variable for different sample indices. But if we actually have temporal structure, we get more information, just intuitively speaking, and it turns out that that changes the situation radically. So in this talk, I will be made, in this talk, I will not actually be talking in any detail about the different kinds of temporal structure. But in what we have been investigating are fundamentally two different kinds of temporal structure. One is autocorrelations, or in general, various kinds of temporal dependencies, which is kind of easy to understand that, you know, two subsequent time points basically tend to have similar values. But then also there's another case, which is the non-stationarity, which is illustrated here in a basic case, which is something like, for example, that the variance or some other statistical property of the signal is changing as a function of time. So like here we have a signal whose variance is very small in the beginning, then the variance goes large here, then it goes very small again, and so on. So in fact, using these two ideas, two kinds of temporal structure, we can prove that the nonlinear ICA model is identifiable, and we can actually recover the original sources. So this was actually done reasonably late. Kind of one of the first papers was by Sprecherl and others. Harmeling and others actually had showed completely like experimentally in simulations that autocorrelations seem to help, or they seem to enable the discovery. The first proof was actually by Sprecherl and others. And then we basically generalized these proofs and also considered the case of non-stationarity in 2016 and 2017. Okay, but I will not go into any detail on that. So just the basic point is that if we have a suitable model of the temporal structure of the independent components, then actually we can identify the model. But then the question is that how do we identify it? Well, of course, maybe the first thing that might come to your mind is to use likelihood, maximum likelihood estimation. And that is actually something that seems to be quite easy at first sight, at least. So here I'm just formulating the basic mixing again with a more specific notation. So now we talk about time series. We have xt is n-dimensional time series, and it is basically expressed as an invertible bijective mixing of n latent variables called the independent components, which are independent. Not independent over time, but the different elements of S are independent. Now, it is actually not very difficult to formulate a log likelihood for this kind of a model. Well, what we have in the log likelihood is basically two terms. The first term here is something that simply gives you, is simply the time series model that you have chosen, calculated for the estimates of the independent components given by these nonlinear functions gi of each of the data points x, x1 to x big T. So here you just plug in your time series model from the previous slide, presumably. So it's either something with temporal correlations or something with non-stationarity. But then we get this second term, which looks simple enough, which comes from the probability transformation formula, which says that when you transform probabilities with the function f, then, well, you will get this determinant of the Jacobian of that function, or actually, well, here I'm using its inverse. Right, and it turns out that this second term is actually very difficult. So here I'm just writing it out again. So suppose that we now model this function g by a neural network parameterized by theta. Then it's a very difficult question how to actually optimize this. It may look simple, but in fact, it's a rather well-known term in a lot of work in machine learning, where basically people have been thinking about how to evaluate this term, and almost always, the prevailing idea in the literature at this point is that it's kind of too difficult. And what you need to do is to strongly constrain the function g. What people do in flow models and so on, which are a special case of this framework in a sense, is that they say that g is has some kind of autoregressive structure, so that it, in which case the Jacobian is basically triangular, because each kind of I hope you understand what autoregressive structure means. Although it's autoregressive not in the sense of the time series I'm talking about here. It's a slightly confusing terminology. But so what they say is that you have like x1 is simply you only make a pointwise transformation on x1. Then you take x2, x1, and x2 and calculate one function of those, then x1, x2, and x3, and one function of those, and so on, which is a very strong constraint on G. But so here, I don't want to make that kind of a constraint because it's kind of against the idea of identifiability. I want to have a case where we can approximate basically any kinds of functions G, because, well, maybe the ICA model is allowed to use any invertible functions f, and thus any invertible functions G. Okay, now, in fact, if you take a classical case where you have a neural network, multi-neural network with square weight matrices, here I denote D times D, well, it could be also N in the previous slides. Well, actually, you get something which again looks reasonably simple. You get something where at each layer you calculate a certain function of the outputs, where sigma here is the output function of the neural network, the nonlinearity of the neural network, and then you get this term log determinant again, but now of each weight matrix in the neural network. Now it looks rather simple, and in fact, the first term here can be optimized by simple backpropagation. But the difficulty is that when you calculate the gradient of this term here, you actually get the inverse of W, well, the transpose of the inverse. And this inversion has cubic complexity, a cubic as a function of the dimension. And that actually, well, if the dimension is like 1000, it is quite annoying because most neural network calculations in backpropagation, they have quadratic complexity. So now you suddenly would have 1000 times more complexity. So the solution that we proposed here is what is called the relative gradient. The basic idea is actually reasonably simple. It's related to what is called the natural gradient. It could be seen as a special case of what Amari-sensei calls the natural gradient. So the idea is that let's consider a multiplicative perturbation. So let's denote by H like any function here. We multiply, which is a function of a matrix. Now, instead of making an additive perturbation, like typically in calculus, we make a multiplicative perturbation like this. Then using ordinary calculus, we can calculate that, well, this is actually then the perturbation multiplied its dot product with an expression which is like this. It uses the ordinary gradient plus then this matrix W. So that is the optimal perturbation. W is then clearly something like this. Now, if you plug this optimal perturbation into the formula, you actually get this kind of a formula. So where basically it's the gradient, this gradient descent or steep descent method is something where you add to W, not the ordinary gradient, but the ordinary gradient multiplied by W transpose W. This is actually theory well known to people working on maximum likelihood of linear ICA. But now the point is that we can actually do this for each layer separately. And the benefit is that, so at each layer separately, then when we calculate the relative gradient of this difficult term, well, it actually simplifies the W itself, which is, of course, trivial to compute. It's not cubic anymore at all. It's not, yeah, it's actually, well, kind of trivially quadratic. So this solves completely the problem of having cubic terms, and we can actually calculate, we can actually optimize the likelihood, noise-free likelihood of nonlinear ICA without any particular computational problems. But in fact, the logic here is much more general. It can be used to any model where we have a likelihood which has a kind of a similar form. In particular, any model where we have this log determinant of the Jacobian term. And as I just said, that's actually what you always get in the normalizing flows literature. So you could actually use this idea there. You don't need any kind of an autoregressive form of the function G anymore. It can be basically anything modeled by this kind of invertible neural network. Okay, so that was the noise-free likelihood. So that's one approach. Another approach would be to use noisy likelihood. Well, this is related to what people call typically deep latent variable models, which in the very abstract form are formulated as follows. So we have again latent variables S and observed variables X, and trivially we say that, okay, the joint density is something where we have the prior distribution of S and then a kind of an observation posterior distribution of X given S, parameterized by some neural network, presumably. Now, in principle, we could just integrate out S, and then we get the probability of X. But of course, these kind of integrals are extremely difficult to calculate, and people usually don't do anything like that. So what people would do in this kind of a case typically is to use something like some kind of variational approximations. In particular, what is now fashionable is to use variational autoencoders. Well, actually, variational autoencoders, it's a little bit a confusing term because people conflate two different things under that term. One is the definition of a generative model, of a latent variable model, and second, a method for estimating it. So I'm kind of doing the same thing here. So first, a typical VAE framework as typically defined, it includes the following kind of a simple latent variable model. We say that the prior S is such that S is white and Gaussian. That means they are Gaussian and the latent variables are Gaussian and independent. And the posterior is actually defined by this kind of a simple formula where you have some nonlinear transformation of the SEs plus N, which is Gaussian noise. And so then the estimation happens by using variational inference, obviously, in particular kind of a version of what people call black box variational inference, where everything is kind of learned automatically so that you don't actually need to do any analytical calculations like you would do in classical variational inference. And thus you obtain approximate maximum likelihood. And so that is actually how we then approach the question of doing maximum likelihood in the noisy ICA case. So what is then the connection between this? Okay, so we see that the inference method is, sounds applicable to the nonlinear ICA case. But how about this model here? Is it somehow related to ICA? Well, in fact, formally, it looks like nothing else than a noisy version of nonlinear ICA. But now it's a very special case of nonlinear ICA where first of all, we don't have any kind of temporal dependencies. And second, even the independent components are Gaussian. So actually the model is kind of catastrophically unidentifiable because it is unidentifiable for two different reasons. First, there is no temporal dependencies, and that therefore this Darmois theory that I talked about earlier applies. But second, it's not identifiable for the second reason, which is that the independent components are Gaussian. And even in the theory of linear ICA, it is known that even a linear transformation is unidentifiable if the variables are Gaussian. So my interpretation is that the original VAE, it is really something like PCA. It does do dimension reduction. The dimension of S can be smaller. It usually is smaller than the dimension of X. But there is a kind of but I think it's a confusion of concepts, a conceptual confusion to think that VAE would be doing something like ICA. There is no guarantee that the components given by VAE are actually any kind of original identifiable components. In fact, as I just said, they are not identifiable at all. So now, how can we, but is it possible to somehow transform this framework so that it is actually identifiable? Well, it is. And we proposed an identifiable version which we simply call IVAE. Well, I will not go into too much details, but fundamentally, we could simply say that the SEs here follow one of the time series models that identifiable time series models that I had previously, either temporal dependencies or non-stationarities. In fact, in this paper, we kind of generalized that theory by assuming that there is some kind of a auxiliary variable U, which could actually simply be the history of the time series or the time index. So in which case it covers the two cases of temporal structure early. And then we make assumptions that SIs are conditionally independent on U. But this is all kind of optional. Fundamentally, the idea is that we just need to make more statistical assumptions on the SEs, the same kind of statistical assumptions as I did earlier, and then we actually transform the VAE model into an identifiable nonlinear ICA model, and we can use a variant of the VAE inference machine to actually estimate the model. Okay, I'm kind of running out of time, but okay, I will briefly then just mention our most recent work, where we basically try to combine all these time series models together. So previously we had non-stationarity and temporal dependencies. Now what we do here is that first of all, we model the non-stationarity by an HMM, which means that we don't even need to know the segmentation, which was actually assumed in earlier models. And then we combine this with temporal correlations in a linear autoregressive model. Well, this is actually, this combination was actually already earlier done by Moria-Kazan in our recent paper. But so here the point is to have like a generative model where we have a separate kind of dynamical equation and a separate observation equation, and we are then able to do maximum likelihood inference of the whole model. And actually, in this paper, one of the main technical contributions is to show that we can have measurement noise of any arbitrary distribution, which is in fact a theory that applies to much more general models and is not really restricted to nonlinear ICA. And so we prove the identifiability of a model, and again show how to estimate it by using a variant of variational autoencoders. And just because so many other people are showing neuroscience results, so I will just briefly mention a simple result on neuroscience, which is kind of what I would call, I suppose I can call it semi-supervised transfer learning. So where we estimate these independent components from resting state data from a number of subjects in MEG. Then we take new subjects, and for those we take data with stimulation modalities, visual and auditory stimulation. And so then we, using these features learned from different subjects, we actually try to learn to classify these two modalities using very limited number of labeled data, and training a linear SVM on these independent components. And we seem to get very good classification accuracy, a bit better than in our previous work. And well, if we had like conventional methods, presumably they would be even worse. Okay, so to conclude, nonlinear ICA is basically a principled approach for representation learning. That's kind of the main claim here, that it's something that's principled. It has a proper theoretical formulation, identifiable formulation, and we can even use maximum likelihood. So it is defined on a latent variable model as linear ICA, and then importantly, it is identifiable, meaning that we can recover the components that actually created the data, unlike PCA and unlike, I would claim, VAE. And for this, we need something like temporal structure or axially observed variables. And importantly now, because of our recent work, basically coming from last year, we are now able to do maximum likelihood estimation of different kinds. Now, self-supervised methods, they certainly have their merits. They may be algorithmically easier and so on, but in fact, we can show that sometimes they fail even when this maximum likelihood estimation works. And well, as a last point, I would like to mention a third approach, which is basically using energy-based models. But well, okay, I will just give the reference. Yeah. Okay, that's all. Thank you very much.
So we have 2 more AIP Open Seminar. So next week, there will be a talk by a business and economics information fusion analysis team led by Hoshino Sensei. And then on September 22nd. There will be a talk by Cognitive Behavioral Assistive Technology team led by Dr. Otake. And if you are interested, please join the future AIP Open Seminar. So yeah, so it's maybe 10 minutes late. And so I'd like to close today's AIP Open Seminar. And so I'd like to thank all the speakers and also all the audience and all people who gave questions and discussion. Thank you very much. So see you.